The first talk is by Shuichi and Hirahara from National Institute of Informatics, Japan, which cares about capturing one-way functions via NP-Hardness distribution.
Thank you so much for giving me an opportunity to give a talk here. So I'm going to talk about the relations between one-way functions and NP-Hardness of meta-complexity. So let me remind you the definition of a one-way function. F is said to be one-way function if it's easy to compute, but hard to invert on average. So it's defined with respect to the notion of average hardness. And a canonical example of one-way function is integer multiplication. Given x and y, you output x times y. If you take the inverse, it corresponds to integer factorization, which is believed to be hard. And this is one of the most fundamental cryptographic primitives because it is equivalent to many cryptographic primitives such as theorem generator, theorem function generator, private key encryption, digital signatures, and the commitment scheme, and so forth. So it's very important to understand whether it exists and what the questions, what is the minimal complexity assumption that characterizes the existence of one-way function. So the main question that we address in this work is whether we can characterize one-way functions by using some worst-case hardness assumptions. And the main result of this talk is to give an affirmative answer to this question. Namely, the main result is that the following two statements are equivalent. The first statement says that there's a one-way function secure against polynomial size circuit. And the second statement is some worst-case assumptions. Namely, NP is hard for polynomial size circuit almost everywhere. And we also require that some problem called distributional common complexity, which we introduce in this work, is NP hard under randomized polynomial term reduction. Remember that the notion of NP hardness is defined in terms of worst case complexity. So these two assumptions are worst case complexity. On the other hand, one-way function is defined by using average case hardness notion, and these are equivalent. So that's going to be the main theorem I'd like to talk to you about today. And informally, in terms of Impagliazzo 5 world, this means that in order to exclude Heuristica and Pessiland, we needed to prove distributional common complexity is NP hard. And this actually exactly characterizes the questions whether we can eliminate Heuristica and Pessiland. So this is the overview of this talk. And in the rest of my talk, I'd like to explain the context of this result. And in particular, I would like to review what our previous approach towards excluding Heuristica and Pessiland, and then I will explain what this theorem actually means. So let me start with very basic, namely Impagliazzo 5 words. I'm pretty sure that you are quite familiar with this notion, but just in case, let me review this. So in his very influential words, paper, Russell classified 5 possible words that are consistent with our current knowledge. So here we have algorithms up to cryptomania, and it's known that one of them corresponds to our world. But currently we don't know which world corresponds to our world. For example, algorithmica is a world in which P equals NP, and in this world we can't construct a private encryption scheme. And the rest of the world corresponds to worlds in which P is different from NP, and these are further classified in this way. For example, cryptomania is a world where there's a public key crypto system, and as far as I know, most of us believe that our world corresponds to cryptomania because there are several public key crypto systems that are believed to secure. But currently, we don't know whether it is true or not. And Pessiland, which is relevant to this talk, is what is called the worst possible world, in the sense that neither we can construct a private key crystal system, nor NP can be solved efficiently on average. Mini-crypto is a world in which we can construct private key crypto system, but we can't construct public key crypto system. And Heuristica is a world where there are efficient heuristics that solve NP on average. In compressed theory, when we say heuristics, it means that it's an efficient algorithm that solves most instances of NP. So in this world, NP is easy on average in the sense that we can solve most NP instances. But on the other hand, it also means that it's impossible to construct a crypto system. So we have purpose world, which and one of them corresponds to our world, but we don't know which corresponds to our world. The ultimate goal of compressed theory and cryptography is to decide which world corresponds to our world. In particular, we believe that some of you might disagree with me, but we believe that our world is cryptomania. So the goal is to show that our world is cryptomania. So what's known about these important questions? Well, currently we know a trivial implication in a sense. For example, if we have a public key crypto system, then we can construct a private key crypto system. And if we have a private key crypto system, then NP is hard on average, which is written here. This NP is not in average P. And if NP is hard on average, then it's of course NP is hard in the worst case. And the converse reaction of this implication corresponds to one of the most fundamental open questions in compressed theory and cryptography. For example, the bottom arrow means that whether we can eliminate algorithmic, namely this question is equivalent to P not equal to NP. And the second implication corresponds to whether we can get the worst case to upper case reduction for NP, namely assuming NP is hard in the worst case, can we show that NP is hard on average? This question is called whether we can eliminate Heuristica from five-possible world. And the third implication corresponds to whether we can eliminate Pessiland. And if we can prove all the implication, then we can establish that there is a public key crypto system. And the main question we would like to address in this work is whether we can eliminate Heuristica and Pessiland simultaneously. So that corresponds to this question, namely, assuming that NP is hard in the worst case, can we show that there is a one-way function or private key crypto system? But currently, there are many negative results, meaning that we need to develop new proof techniques. Namely, for example, in order to prove P versus NP, there are many barriers. So we need to develop proof techniques that overcome these barrier results. Similarly, in order to eliminate Heuristica, we need to develop proof techniques that are not subject to relativization barrier, limits of black box reduction, and the impossibility of Hardness amplification. So we need to develop proof techniques that overcome these barriers. And recently, there is an emerging paradigm, as you know, which is metacompressity, which makes us more optimistic. And metacompressity refers to the compressive problem asking about the compressity. And there are two important metacomputation problems, MCSP and MinKT. MCSP is a problem of computing the circuit complexity of a given truth table of a Boolean function. And MinKT is refers to minimum time bounded problem complexity problem. And this is a problem of computing the minimum time bounded minimum program that computes a given program, given string. And by considering these questions, let me now describe previous approach towards excluding Heuristica from five-possible world. A couple of years ago, I was able to prove that for MCSP or MinKT, worst case and average case compresses are equivalent. So remember that there are two important notions of compressity in compressed theory, namely worst case compressity and average case compressity. In the case of average case compressity, we measure the expected running time of an algorithm with respect to input distribution. So that's denoted by average VPP here. In this result, we consider a uniform distribution over the truth table of a function. And for MCSP, computing the such complexity of a given random truth table, it's on average is equivalent to the worst case complexity of approximating MCSP. Here, gap refers to the fact that this problem is defined with for approximation of such complexity. And what's important about this result is that this overcomes limits of black box reduction. And what it means is that Bogdanov-Handel-Trevisan shows that if you consider any problem that is reducible to distributional NP by using non-adaptive reduction, then that problem must be in NP/poly in the core NP/poly. And there's a conjecture saying that gap MCSP shouldn't be in core NP/poly. So under this conjecture, this kind of worst case to average case connection cannot be shown by using a standard notion of reduction, namely black box reduction. And this is a result that goes beyond this limit.
Why it's not equal?
So British conjecture that this is not in core NP/poly, and the argument is that there's a candidate pseudo-random generator secure against core non-deterministic polynomial size circuit. So there's a specific candidate based on subset sum problem, and it's believed to be hard even against the core non-deterministic.
Really quick follow-up. What is special about the subset sum problem in this context? Like, is it only subset sum? Or?
I think there should be many candidates, but the reason he mentioned the specific candidate is that there is no proof system that repeats that. So yeah, for some specific type of proof system, I think there is a lower bound for that.
Is it really an if non lifter? Is it the same?
Yeah, there's a gap, but we can it's
the same gap? Like it's the same?
Well,
in both directions.
For MSSP, in the case of average case complexity, we consider the exact version. But I think we can also consider a promise version. So if you, it's not the same gap, but
I don't see like this direction. Like if it's about an average, what is the final sequence? The gap.
Yeah. It's basically it's equivalent to natural property. So using the fact that there are few yes instances, you can prove the converse relation. So assuming that gap MCSP is hard and computing on average, it's hard to compute MCSP exists. But let's go. And this gives our approach towards elementary heuristica. Let's consider this implication, which corresponds to whether we can prove NP-Hardness of MCSP, gap MCSP. And if we can show that gap MCSP is NP-hard, it means that assuming that NP is hard in the worst case, gap MCSP is hard, then this gives, if we can prove that, although this is a big open question, we can combine this worst case to average case reduction, and we can conclude that assuming NP is a worst case hard, then NP is hard on average. So this gives an approach towards elementary heuristica. Namely, if we can prove that gap MCSP is NP hard, then we can eliminate heuristica. That's the approach. That's a previous approach about elementary heuristic. Okay, now let me talk about approach towards eliminating Pessiland. So as you have heard in morning, a recent very influential result by Liu and Pass characterized the existence of one-way function and average case hardness of min KT. And actually, there's a more classical result, which is a very nice result by Impagliazzo Levin, which characterizes the existence of one-way function with respect by using some problem called T time bounded universal probability, the hardness of the average case hardness of T time bounded universal distribution with respect to any polynomial time sample distribution. So the main difference is that in the Liouville result, they consider a uniform distribution, but in the case of Impagliazzo-Levin's result, they consider any polynomial time sample distribution. And this T time bounded universal probability, which is written denoted by Qt, is somewhat similar to time bounded Kolmogorov complexity, and it's defined to be the probability that a random program D prints X. That's the definition of universal probability. And actually, if you know the notion called probabilistic Kolmogorov complexity, which was recently introduced, if you take minus log of this probability, it's almost equivalent to probabilistic Kolmogorov complexity. So you can think of this as a time-bounded, a variant of a time-bounded Kolmogorov complexity. Now, by using this result, we can describe a folklore approach towards eliminating Pessiland. Namely, if we could show that Qt is NP-hard under efficient reductions, then we can eliminate the Pessiland. Actually, this is the approach that Yanni described, and yeah, this can be seen by as follows. Let me explain why this is the case. So NP-hardness is a notion that is defined by using worst case complexity, but if it's NP-hard under efficient reduction, here we require that the running time of the reduction is much smaller than T, where T is a time bound of the Qt. Then by using this reduction, we can induce some distribution over instances on which Qt is distributional NP complete, distributional NP hard. So we can get some hard distribution such that the Qt is distributional NP complete. Then by using Impagliazzo-Levin's result, and this result says that if there is no one-way function, then you can solve Qt on every sample of the distribution. So you can solve this problem on average. So that's how we eliminate Pessiland. So so by combining these results, we can describe a previous approach towards eliminating both heuristic and Pessiland. This worst case average reduction actually works for Qt as well. So if we could prove that gap Qt, which is an approximation problem of Qt, then we can eliminate both heuristic and Pessiland. But unfortunately, there is a gap, small gap between the notion of average case complexity, and this doesn't imply that we can prove the worst case hardness of NP implies one-way function. The reason is that in one of this result, we consider errorless average case complexity, which is denoted by average P. And on the other hand, in the case of Impagliazzo-Levin's result, we consider error-prone average case complexity, which is denoted by P. So let me explain the difference between these two notions. So there are two notions of average case complexity. So we can, depending on the notion of average case complexity, we can define variants of Impagliazzo fibers. Namely, if we consider average P, we can define errorless heuristica and errorless Pessiland. And average P here means that it's solvable by an errorless heuristic scheme. And this means we say that the distribution problem is in average P if there is a errorless heuristic scheme such that the errorless heuristic algorithm outputs correct answer, or if it makes error, it must output a bottom symbol. And we also require that the probability that it fails is at most delta. So this is errorless notion in the sense that when you make error, you must output that the algorithm makes error. And this is known to be equivalent to average polynomial time. So you can define by using expectation of running time of algorithm as well. And similarly, there's a different notion called error-prone average complexity, or Heuristic, and we can define error-prone Heuristica and error-prone Pessiland. And the difference is that in the case of Heuristic, we just consider a standard notion of heuristic scheme, which means that we don't require the errorless condition, and we just require that the probability that algorithms fail is at most delta. So that's the difference. And currently, so there might be a gap between errorless average complexity of NP and error-prone average complexity of NP. So if we could prove that NP hardness of Qt, time-bounded to universal distribution, then we can eliminate errorless Heuristica and error-prone Pessiland. But there might be, it could be the case that our world corresponds to errorless Pessiland intersect error-prone Heuristica. Namely, it's errorless Pessiland in the sense that NP is hard with respect to average P, but NP is easy in the sense of error-prone Heuristica. Unfortunately, currently we can't rule out this possibility, and even if we could prove NP hardness of meta complexity, it might be the case that we can't base the security of one-way function on the worst case complexity of NP. So this is one problem in the previous approach. But actually, there is another fundamental difficulty, which was recently identified by very nice work by Sachs and Sansalan. So what they showed is that under some plausible assumption, actually, gap Qt is not NP hard, and if you consider efficient reduction. So remember that in the current approach, if we could prove that gap Qt is NP hard, then we can heuristic and Pessiland, but we don't know whether this is plausible or not. And in particular, what Sachs and Sansalam showed is that if the gap is additive omega log n, then this assumption is actually not plausible. So if we consider this approach doesn't work, especially for Pessiland. So that's another fundamental difficulty in the previous approach. So to summarize the previous result or previous literature, there are several important open questions that are left unanswered. So the first question is whether the approach of using meta complexity necessary. Another question is whether there is a meta complexity problem whose NP hardness is sufficient for excluding Pessiland. Remember that in the case of Qt, if we could prove that it's NP hard, then we can eliminate Pessiland. But unfortunately, it's likely to be false. So we need to come up with other meta complexity problem. Another question is whether we can close the gap between errorless and error-prone average complexity. The main contribution of this work is to answer these open questions as follows. For the second open question, we can, instead of Qt, we'd like to propose to consider distributional Kolmogorov complexity. And we show that NP hardness of distributional Kolmogorov complexity is sufficient for eliminating Pessiland. And for the first question, we can show that it's necessary in the sense that if we can eliminate heuristic and Pessiland, then actually NP distributional Kolmogorov complexity is NP hard. So in that sense, NP hardness of distributional Kolmogorov complexity is necessary. And for the third question, we can't still close the gap unconditionally. But if we assume that distributional Kolmogorov complexity is NP-hard, then we show that the gap can be closed in a certain technical sense. Any questions so far?
You already have
well, in the proof, I needed to close the gap between errors and the average complexity. Yeah. So if we can consider one function, we can close the gap, and that's a technical complexity. Okay. So now I'd like to introduce the notion of distributional Kolmogorov complexity. So let me review the notion of Kolmogorov complexity. So the Kolmogorov complexity of a string X, which is then K of X, is a X of a shortest program that prints X. And an example is that if you consider the Kolmogorov complexity of all 0 and n-bit string, then the Kolmogorov complexity is at most log n plus a little constant, because there is a small program that says print 0 n times. And we can also define conditional Kolmogorov complexity of a string X given Y. And this is defined to be the shortest length of a program that prints X given input Y. That's the notion of conditional Kolmogorov complexity. And naturally, we can consider T time bounded Kolmogorov complexity, which is the length of a shortest program that prints X in time T. And now let me define T time bounded distributional Kolmogorov complexity of a string X given distribution D. So this is a natural generalization of conditional Kolmogorov complexity. In the case of a conditional Kolmogorov complexity, we consider a fixed string Y. But in the case of distributional Kolmogorov complexity, we consider a distribution over conditional strings. So distributional Kolmogorov complexity is denoted by in this phrase, and this is defined to be a shortest program M, the length of a shortest program M, such that if we take a random string from the distribution D, then the probability that M outputs X given the input Y is at least lambda, where lambda is a parameter given to the distributional Kolmogorov complexity. So that's a definition of a distributional Kolmogorov complexity. And in particular, this generalized conditional Kolmogorov complexity in the sense that if you consider a singleton distribution of Y, then this is equivalent to conditional Kolmogorov complexity.
Shuichi?
Yeah.
Is there any distributions I should have in mind that would be useful for me to think about?
Yeah, not so clear, but yeah, for example, in the case of uniform distribution, this is equivalent to randomized Kolmogorov complexity. So if you consider uniform distribution, the program gets input as input, you get a uniform random string. And in that case, you can think of this as a randomized program. So in that case, this notion is equivalent to randomized Kolmogorov complexity. So that's one notion. Yeah, that's right. Yeah, M must run time T. Yeah.
Right? I mean, the solution is independent of X. So it explains motion. I mean, why did solution help you if it's like so many X?
Yeah, I think that's a good question. Yeah, the reason I needed to introduce distributional Kolmogorov complexity is that I'm not sure how to prove NP-hardness of the distributional Kolmogorov complexity. Yeah, ideally we'd like to say that conditional Kolmogorov complexity is NP-hard, but currently we don't know. So yeah, in the proof, we prove that by constructing some distribution, it's NP-hard. But in that case, it helps.
And the distribution depends on X.
Yeah.
No.
Well, given Y, if you look at X given Y, it can be
Yeah,
Y
but
that's
these
related
like
to X.
could these are fixed. You want to fix these.
I'm not sure. I mean, it is. I mean, maybe X is chosen as a function of a string X given some distribution related to X.
Oh.
Yeah,
It's independent of the particular Y.
okay. In NP-hardness proof, D depends on.
These are dependent. Okay.
Yeah, yeah. Okay, so
How is D given?
oh yeah, I will explain that. So this is just the definition of the distribution from complexity. Now let's consider meta complexity version of distribution from complexity, which I call gap MDKP. So this is just a problem of approximating distribution from complexity, and this is a formal definition. So you are given a string X, and you are given a distribution D, which is represented by a circuit, Boolean circuit. And in this way, you can describe a distribution as an input. And you are also given a size parameter S and a success probability, lambda. And your task is to decide whether it's yes case or no case. And in the yes case, distributional complexity of X given D is at most S. That's a yes case. And in the no case, distribution complexity is at least 1 plus epsilon times S, where epsilon is any constant, and the time bound is a polynomial.
So the time bound in both cases are the same?
Yeah, that's the same. Yeah, there is no gap. But for success probability, we allow some small gap. And you can easily see that this problem is in promise MA. And that's a problem we consider. And for some technical reason, actually, I needed to consider Oracle version of this problem, which I call MDKP to the A. But we are going to consider Oracle in P-search poly. So you are given an efficient Oracle, and you want to decide whether distributional complexity with respect to A Oracle is small or not. I haven't defined what is Oracle version, but since this is a can be described by polynomial size circuit, you can think of this as a follows. So distribution complexity of X given D and A is small or not. So what we show is that if this problem is NP-hard, then we get a one-way function.
Shuichi? Should I be thinking that this this p-poly thing is related to the fact that one-way functions are secure against non-uniform circuits?
Yeah, exactly. That's a very good point. So the reason why I need to have this is that this intuitively, this Oracle polynomial size circuit can be thought of as an adversary for one-way function. And if we can prove that this problem is NP-hard, then we can consider one-way function that is secure against the polynomial size circuit. Yeah.
Input now or not?
It's not an input.
It's not an input.
So
So
A
what
is
does it mean
chosen
that it's
adversary
NP-hard? That's NP-hard for some A. Or
for any. Yeah, I will state it in the next slide.
So also I didn't get it. So it's either you're not getting A or you're getting A.
No, we in the reduction we don't have access to A. Okay, let me state the formal statement of main zero. So we can prove the following equivalent for any constant. The first statement says that there is a one-way function secure against P-search poly. And the second statement is that NP is hard in the worst case, and 1 plus epsilon factor approximation of distribution complexity is NP-hard. Let me state it more formally. So the meaning of this NP-hardness is that there is a parametric honest randomized non-adaptive reduction from NP to gap MDKP problem, which I defined in the previous slide, for any polynomial tau and any polynomial size circuit A. That's a formal.
reduction is independent of the Oracle A.
Right, that's a very important point. So this reduction must not depend on any polynomial and any Oracle. So the reduction must be independent of tau and A. So in particular, this means that the running time of the reduction is sufficiently smaller than tau, where tau is the parameter of distribution.
Don't say anything about the size of the circuit that is tried to distribution.
Yeah, as long as it's polynomial size, it's fine. I mean, yeah, that's in the part of the input to MDKP. So yeah.
plausible assumption under which this hardness result will work for every A, not just A. Is there a plausible assumption under which this gap MDKP is NP-hard for every A, not just for A?
Oh, I see.
Because I mean, in practice, how do you use the fact that A is pretty much more? It's not that hard.
Yeah, that's great. Good question. I'm not so sure.
I guess the plausible assumption would be there's a one-way function.
But the assumption is not clear as well for every A.
Yeah. In the proof, currently we need to exploit the efficiency of it. So if A is not in P-sorry, I'm not sure how to do it. Yeah. So the question is whether we can get rid of this P-sorry condition, but I'm not sure.
That's asking whether that's an oracle kind of area.
Oh, yeah. That might be good. Yeah.
Any intuition that the second barrier doesn't work for DKT?
That's a good question. So intuitively, in the standard transform result, they crucially exploit that you are just given a string. So the input to Qt is just a string, and you want to know whether it's compressible or not. But in the case of distributional Kolmogorov compression, we are given X as well as a distribution. So it's a kind of conditional version. And in some sense, we can encode information about the NP instance into the conditional string. That's the idea. Yeah. In the case of a conditional Kolmogorov compression, standard transform barrier doesn't work. So that's it.
Also, like, it's the auxiliary input one.
Well, in the proof, I needed to go through the notion of auxiliary one function, but I'm not sure about the
Is the following a good way to describe it? So like this gap problem for any A in P/poly, this is going to be an P/poly, right? Yeah. So, maybe one way of saying it is that this is you want to prove that this gap problem is complete for NP-poly in a certain sense.
Yeah, that's right. Yeah, this problem is in MA/40, and yeah.
Yeah. So with a P/poly work, that whole thing be in P/poly. Everything is in P/poly. You're basically trying to prove this problem is in P/poly in a particular sense. And that's equivalent.
But if it just comes along, rather than random.
Yeah, actually, I need to consider randomized reduction. Yeah, actually, if you consider non-uniform reduction, I think we will get auxiliary into the characterization of auxiliary ones. Yeah.
So in some sense, the reduction is going to be a one function, right? Or is that the?
Yeah, that's right. Yeah, that's correct intuition. So if you consider any reduction, this translates to one-way function. So the construction of one function comes from the reduction. So that's the idea of the proof.
It's not really a single problem then, that it's because since it's parameterized by the attacker A in some sense, right? So it's
No, the reduction must be.
no, the reduction isn't. But I'm just saying, like, it's not a single problem that you're showing NP complete, so that problem characterizes one functions.
It's not
Because
a single problem.
it's for all the.
Yeah, it's a crossing problem. If you can prove NP-Hardness will cross over this problem, then we get the problem. Okay, let me try to state this as in terms of Impagliazzo fiber. Basically, this result can be also stated as saying that NP-Hardness with distribution complexity characterize the question of eliminating Shuichi and Pessiland in this formal sense. So instead of having the condition that NP is hard in the first case, we can consider assuming that NP is hard in the worst case, namely our world is not algorithmic with respect to polynomial circuit. Then the following equivalent. There is a one-way function secure against P/poly, meaning that Shuichi and Pessiland do not exist, and distributional Kolmogorov. This is equivalent to distributional Kolmogorov compressive NP-hard, which means that we have an NP-hardness of meta compression. So this characterizes the approach of using metacomplexity is complete for eliminating heuristic and Pessiland. So I don't have time to explain proof techniques, but the current proof technique, the current proof is very complicated. But one direction, namely NP-Hardness of distributional complexity, and assuming the existence of one-way function isn't so difficult. And this is similar to NP-Hardness of proving partial MCs. And the compass is very complicated, and we need to combine a lot of results. But the high-level idea isn't so complicated. Basically, at the high level, we just combine a very nice result by Miki to Nanashima and my worst case case reduction. So what Nanashima showed is that if NP reduces to avoiding a hitting set generator, which is a stronger notion than one-way function, by using a black box reduction, then we can eliminate the heuristic and Pessiland. That's what he showed. On the other hand, in my worst case average case reduction, we showed that K-poly, time-bounded complexity problem, reduces to avoiding a hitting set generator by using a non-black box reduction. So the first step in this work is to generalize this result to distributional Kolmogorov complexity. So for distributional complexity, we can also get a similar worst case to average case reduction. And then we are going to combine these two results, but there is a gap between black box reduction and non-black box reduction. So the most of the paper is devoted to combine these proof techniques. Namely, assuming that distributional complexity is NP-hard, actually the gap between non-black box and black box reduction can be closed in a certain formal sense, and that's what is happening in the paper. And let me mention how we can close the gap between errorless and error-prone average complexities. And this is actually identified in the work of Nanashima. And the key idea is that it's to use that one-way function is testable in the following sense. Let's say you are given an oracle access to A, where A is an oracle that tries to invert one-way function. And the condition that A inverts one-way function can be written in this way. And the key point is that this condition can be tested in polynomial time. So by choosing X randomly, and you can check whether A inverts one-way function or not. And in this sense, one-way function is testable. Now, at some point in the proof, I need to construct errorless heuristic scheme. And the way I construct errorless heuristic scheme is that we use this testability. And if an oracle doesn't invert one-way function, then we output the bottom symbol. That's how I close the gap between errorless and error-prone averages. And I don't have time to explain metacomplexity padding conjecture, but in the paper I propose some conjecture which I call metacomplexity padding conjecture, which says that time-bounded Kolmogorov complexity is reducible to distributional Kolmogorov complexity by using approximation preserving padding reduction, which means that the size parameter can be increased in a certain sense. And under this conjecture, we can show that we get a nicer characterization of one-way function by using the hardness of gap MCSP and the time-bounded Kolmogorov complexity. So if this conjecture is true, then we can show that there's a one-way function if and only gap MCSP is hard in the worst case. And more generally, it is interesting to see whether metacomplexity problems are paddable or not. And actually, in the case of formal MCSP, we can get a padding reduction. By using KRW conjecture for parity, we can increase the formula complexity of a given function by taking a composition with parity. And it's interesting to see whether we can get a similar padding reduction for MCSP. So yeah, thank you so much for your attention.
My panel is setting up. There are more questions.
paragraph of proving it had it as the oracle independent paragraph.
No, I just know. For my function, then we can put it.
Shuichi, when you showed that this DK problem is instead of showing it as
So it's
if you prove that DK poly was it's not poly or something like that. Heuristica say or
Yeah, if distributional protocol is a card, then Heuristica can be extended. And we have a basket targeted distribution.
but Pessiland, I guess.
Yeah, for Pessiland, yeah, you need to efficiently.
Okay, so let's listen to today's last speaker, Andrew Grant from Oxford University. And, still in the theme of crypto meta complexity, he'll tell us about the cryptographic approach to the NP-Hardness approximating meta complexity.
Thanks for introducing.
This is a